Hello, I am Jack Sifri, a Mimic Design Flow Specialist at Keysight Technologies. In this short video, I will show you how to use the design of experiments methodology to help you create and produce robust designs with first-pass success and high yield. This way you can eliminate design iterations and save an enormous amount of time and money. For example, look at this two-stage LTE Mimic power amplifier with its 5 subnetworks. The design works very well with its nominal component values. But when I ran yield analysis with plus or minus 5% on all the components, notice the huge variation in the output power with many failures and low yield. A design of experiment was implemented in order to find out the source of this serious problem in the yield. DOE pinpointed the problem, I fixed it, and now look at the final yield analysis on the fixed design. Later on in this video, I will come back to this example and show you how I conducted this DOE analysis. Now, please allow me to give you a very brief introduction to DOE. Let's start with a simple amplifier circuit, and let me select 3 variables that affect the output gain of the amplifier. These 3 variables are the 10 micron line width shown in red, and the 20 ohm resistor R, and the 10 picofarad capacitor C. In DOE, we vary these variables by a small amount, let's say plus or minus 5% on the resistor and the capacitor, and plus or minus half a micron on the line width. After doing that, we run experiments on all possible combinations of the plus and minus parameter values. So for our 10 micron nominal value line width, a minus 1 corresponds to 9.5 micron, and the plus 1 corresponds to 10.5 micron. 3 variables we have requires 2 to the 3rd experiments, requires 8 experiments to cover all possible combinations. So we run these 8 experiments and we record the amplifier output gain at the far right column. Now that we have collected all the data, let us see the main effect of the capacitor. So what we do is we average the minus 1 output gains shown in yellow and the plus 1 output gains shown in blue for the capacitor only, and we determine the change in gain. Here it is shown 0.09 dB, which is very small. Therefore, we conclude our output gain is not sensitive to capacitor C. Next, we repeat the same procedure for resistor R. We average the minus 1 output gains and the plus 1 output gains for R only, and we determine the change in gain. Notice here the change in gain is much bigger. It's 1.69 dB. This already tells us that our output gain is very sensitive to the resistor R. Now, what is nice about DOE, it also determines the interactive effects of variables. For example, here we repeat the same process for the interaction between the width of the line W and the resistor R, and we find out its contribution to the output gain. At this time, I strongly encourage you to read the document I'm providing to you at the end of this video to learn much more about the DOE mechanics. It is an easy read document that explains DOE in more details. So after determining all the main effects and all interactive effects, we then plot them all on a Pareto chart to help us visualize and pinpoint the biggest factor that affects our output gain. And here it is. You can see it is very clear the resistor R changes our output gain drastically and must be controlled. So how do we do this in this simple example? If R is a surface mount resistor on a board design, we could pay a bit extra money and screen that resistor and control it to plus or minus 1% variation instead of plus or minus 5%. That is one way to fix the problem and reduce its effect. But if it is an IC design, one way to control the tolerance of the resistor is to lay it out larger in width. This way, a plus or minus 0.5 micron variation in the width has less effect on a wide resistor than on a skinny one. Of course, the trade-off is it does take more area on the IC chip. So now, let me take you back to the original LTE mimic power amplifier design I showed you at the beginning of this video, and let me walk you through the setup process in running the DOE analysis on it, and show you how DOE would determine which component in this design impacts the yield. This is the LTE mimic power amplifier workspace in ADS. As you can see here, folder number 1 contains the initial design. So if I open the schematic, you can see the 5 subnetworks. And I will show you at the end of this video how to get a copy of this design. So when you get a copy, you can push into the subnetworks if you wish and check out the design. So the initial design, if we simulate it right now, click on simulate, it initiates the simulation, and this is the P-in, P-out curve, the input and output power curve, and you can see it is very smooth and compresses nicely and meet our specification. It gives greater than 26 dBm when the input power is 2 dBm. Folder number 2 contains the yield analysis, Monte Carlo yield analysis. So when I simulated, this is the output that I got. And you can see clearly that there is a wide variation in the output power, and there is many failures, as you can see here. So definitely there is a problem in the design that we need to investigate and solve before going into production. Folder number 3 contains the DOE analysis. And notice I have 2 different DOE analysis. I am going to show you the DOE analysis done on 6 capacitors, on capacitors. So if I open the schematic, I see the same exact design. The only difference now is I have DOE controller and DOE goal. How did I get this controller and goal? It's from the pull down menu. You go to optimization, statistics, and DOE. Notice here there is the DOE controller and the DOE goal. So I placed these on the schematic page. And notice here for my DOE goal, I asked to look at the output power, Vout dBm. And Vout dBm is right here at the output node. Other than that, all you have to do is select your variables like I showed you before. In this case, I have C1 input matching network, C2 input matching network, and I assigned a DOE plus or minus 5%, plus or minus 5%. I do the same thing to the interstage matching network. I have C1 and C2, and I have 2 more that make 6 capacitors total at the output matching network. So I have 6 capacitors, 6 variables. Now to run DOE experiment on 6 variables, I need to run 2 to the 6th, which is 64 experiments. And notice when I click on simulate, you will notice that ADS will automatically and quickly simulates the 64 trials. Let's do that. See, here are the trials: analysis 11, 22, 44, 54, 64. And here are the results. Notice in the Pareto chart, it is telling me that 100% of the problem in my design, the yield problem I have, 100% is coming from C2 interstage matching network. Capacitor C2 in the middle, in the interstage matching network. And because of this C2 interstage matching network, it is telling me it's causing my power to fluctuate between 27 dBm down to 12.5 or 13 dBm. So C2 is really the big problem that's causing the yield problem in my design. On the layout, here is C2 in the interstage network. It is this series capacitor that is causing the entire problem in our design. Now that I know C2 is the problem, I utilized the yield sensitivity histogram templates in ADS as shown here. Basically what I did, I put the variable C2 interstage matching network, and this tells me that C2 interstage matching network nominal value is 7.6 picofarad, and it changes plus 5% and minus 5%. And notice when it is a lower value, my yield goes 100%. But if it goes higher value, the yield goes to 0. That means it is less than 26 dBm for the power output. This is really telling me that all I have to do is just lower the value of C2 and it will fix the problem. It will give me 100% my overall yield for the whole amplifier. And this is what I did. Let me show you. I went ahead in the final design here. I changed C2 as shown here to 5 picofarad from 7.6 to 5 picofarad and re-optimized my circuit. After I did this, let me show you the final yield analysis that I ran. So you can see now my final yield analysis shows very consistent, no big variability, everything is passing and it is exceeding above the spec 26 dBm. And now I have full confidence to take this design into production. As you have seen, the DOE process does require some time, not only to discover the troubled area in your design, but also to fix it and make it much better. And the reward is achieving first pass success with your designs and saving an enormous amount of time and money. You can get the project file I used and a PDF document on DOE by clicking the link in the text description associated with this video, or by directly using the URL link shown. Thank you for watching.